All right, hello everyone, and welcome to lecture number 3 on stateless services. Last time we talked about web server frameworks and dynamic web pages. We showed how we can build a framework that allows you to write an application to decide how to give responses to HTTP requests and deploy that within a web server that easily allows that code to be concurrently executed on a machine that has multiple cores. We talked about HTTP, the Hypertext Transport Protocol, as the most common type of service that's used, for web pages, but also for all kinds of machine-to-machine interactions, as well as used on the web for websites. With HTTP, a client requests a document, which is specified with a path or a URL, and the server sends back some kind of document in response. So it's like a client-server protocol for fetching documents, and we'll use it for all kinds of things. We gave a high-level overview of Wikipedia's architecture. So Wikipedia, the open source code for Wikipedia is called MediaWiki, and we're going to talk more about that today. And I showed some examples of dynamic web code that renders HTML in a dynamic way for a few different sample websites that I've written over time. Okay, so this was a picture I showed last time of my sloppy drawing of what a web server framework might look like, where your app is one of these is replicated in multiple copies on the inside, and allowing your code to give responses in parallel to multiple requests that come in through a request queue and to give responses out in this response queue. Now, every request goes to a copy of your code, of your app. Now, does it matter which one of the instances of your app is chosen to handle a request? I want you to stop and think about that. It's actually a little bit of a tricky question because it depends on how your app code is written. And in this lecture, we're going to talk about that choice of whether you make your app stateless or stateful. This is a very important concept that affects the overall architecture of your system, so it's worth spending some time on. Okay, so we're going to start with some definitions. So a stateless thread or process or service or applications, or in general code, if it's stateless, what that means is that it remembers nothing from past requests or past executions. So state is, just a fancy computer science word for memory, or the values stored in memory, or the values stored in variables. So if that all is cleared out and every new request is handled with a blank slate and no memory of what happened previously, then what you have is a stateless service. So in such a case, the behavior of the code is determined entirely by just two things. So first of all, the input that you got, and secondly, the logic of your code that's handling that input. So your code, which is written and stays, once you run your application, the code doesn't change. So that second part is going to be the same throughout execution. But then different inputs come in. But for any particular input, if it's the same as some previous input, it should give the same response. Well, actually, that's not totally true, but that's almost true. I'll talk about why that's not the best definition in a second. But the point of this in a scalable system is that if you have different copies of your service running, like on different CPU cores on a single machine, or if you have lots of machines that are in parallel running your code in the horizontally scaled system, those different copies of your service are kind of equivalent. They'll give the exact same response for a given request because, as defined here, all that matters for the response is what the input was and what the code is. In other words, there's no state on those different copies of the service that could be different, so that would allow them to behave differently. So the fact that a given copy machine A running your code received a certain history of requests beforehand, whereas machine B just started freshly, that shouldn't matter when a new request comes in, when that request is sent to machine A or machine B, regardless of that history of machine A running previous requests previously. they should still give the same response. There's no local state. The reason why we can, if the code is written in such a way that there are no variables that store values that are available from after a previous execution stops, a previous response is given, then it's not going to be possible for the behavior to change. Okay. There's no local state, and I emphasize the word local because in practice, there's the system as a whole is not really usually going to be stateless, because any interesting system remembers, stores data and remembers things about what previously happened to implement something useful. But we're going to end up storing that state either up in the client or down in the database in order to make pieces of the system stateless, like that middle, the actual application stateless, and to allow that part to scale. And we'll see how that works later throughout this lecture. Okay. So to contrast with stateless, a stateful thread or service or code or process changes over time as a side effect of handling requests. So a stateful thread can have persistent global variables that can be modified as execution happens. So if a stateful application, as it's handling requests, can have global variables that change, and then the values of those variables can be used to decide how responses are given, and that like memory that it has, we call that state. And I'll have a couple of examples throughout this lecture to clarify this, and you'll see why this is important later on. So just to define this a little more concretely, stateless code has no long-term memory. It's almost like a pure function in programming language terminology, which is to say the output's not affected. The output's not affected by previous inputs. It's not quite the same as saying that the output is determined entirely by the current input, because we allow for non-determinism, which is to say random behavior. So a stateless code is not going to give the same result for if you give it the same input. That would be a deterministic stateless code. So a stateless code can have random behavior, but like that, the random behavior has to be independent of previous executions, previous code, the previous requests that went to that service. So examples of stateless code are things like pure mathematical functions like cosine and sum. If you're summing two numbers, that's always going to return the same thing. That's just a function of the input. The cosine of a value should always be the same thing. Sorting a list should always return the same thing, regardless of what happened previously. Modification of a data structure. If the data structure was passed in and it's passed out, that's the semantics of that function. That also is stateless. This last one is a tricky one. Generating a random number. That shouldn't really depend on previous execution or any history of the program. In practice, real random number generators do keep some state because of the way they work, but that's because real random numerators are not truly random; they're pseudo-random, and so the fact that random number generators are not stateless is actually a sort of a defect in the implementation rather than something that we actually want. Okay. Right. So to contrast with that, stateful code has side effects. So when you run the code, there's something remembered in the system that can affect future execution of the code. Has long-term memory. So this can happen if you have an object that has instance variables that can be changed, or if you have global variables. So an example of stateful code is like, this object, using the object-oriented pattern for a counter. So a mutator in object-oriented code modifies an object, right? So a counter it could be implemented in an object-oriented language like so. So we have the constructor that initializes some instance variable count to 0. This is in Java. And then there's an increment method that increments that variable, right? So this increment method is stateful because it has side effects. The side effect it has is that it modifies the state of the counter. So this count variable on the outside is a sort of is state that's carried over. So when I call increment a second time, the result is different than if I had just called it once. Another, you can get the same effect without object-oriented programming using global variables. So here we have a count variable that's global, and then an increment function in this is just in plain C that increments that count. Cool. Now, that brings me to one little lesson I want to give you on object-oriented programming. It relates to state, and I want you to actually stop and think, from what you know of object-oriented programming, what do you think the main purpose of object-oriented programming is? I know this seems like a little bit of a digression, but I have a little lesson I want to give here, a mini lesson related to state. So think about that for a second. My guess is that you came up with these two things, one of which I think is important, the other one is not so important. So inheritance is the thing that I think you probably, almost everyone learns about when learning object-oriented programming. And that is actually, in my opinion, important. So with inheritance in object-oriented programming, you have a series of types that you can have subclasses that inherit from parent classes. And this allows you to have strong typing in your code without losing abstraction, which is to say you can have a code that accepts, let's say, a string as an input, but then you can have a specific type of string, different subclasses of string that have different implementations and different additional methods, but then you can still define functions that operate on generic strings, regardless of what specific type they are. So that's a benefit of object-oriented programming in inheritance. You can create generic abstract interfaces, but then also have strong typing with specific details exposed when you need them to be. Another thing you might learn in object-oriented programming is it allows you to model things in the real world. For example, you have a cow is a mammal and also is an animal. That's a hierarchy of type. I think a lot of object-oriented programming lessons focus a lot on this, even though this is not really super useful, except only to the extent that it impacts this inheritance concept that is important. There's a second big thing about object-oriented programming, which I think you probably didn't learn, which I want to tell you about now. Okay, so in my opinion, the really one of the really essential, important benefits of object-oriented programming and why it's still used and when it's useful is when you need to have side effects. You need to have something like global variables, but you want those global variables to have well-defined limited scope. So when you create an object, what that does is it groups a set of related state, the instance variables of the object are all grouped together, and they're available to certain functions, the instance methods of that class, but only to those instance methods. So you can have a set of methods, a set of functions that have side effects on a limited set of variables, and those are the instance methods and instance variables of the class. So side effects generally can create code that's difficult to reason about and to prove correctness of. If you run code, global variables are generally frowned upon for that reason. But when you need side effects and something like global variables, an object is a way to limit the impact of those side effects and that global state to just the functions that need to use them. Okay. And side effects are really essential in code that is optimized for high performance. If you're reusing buffers or you have a thread pool or something like that. And that's why object-oriented programming is still a very important paradigm, even though it's harder to prove correctness compared to, say, functional programming. Okay, that was my side note. So let's move back on with the main lesson on stateful versus stateless services. So the reason we're talking about stateless code, mainly is because it's closely tied to horizontal scaling. And remember, horizontal scaling is really the only way we can create a truly global scale system, a huge scale system. We need to be able to run our code on lots of machines. So if we want to run copies of our service in parallel to handle lots of requests, let's look at the two different options, right? We either have code that is stateless or it's stateful. So in the stateless case, we have code that has no memory. That if that's the case, then all copies of our code will give the same response to a request, even though the different copies of the code have have over time received a different history of prior requests. So it doesn't matter which of our copies gets a given request. That's a good thing because it makes parallelism trivially easy. So we have a bunch of work to do. We have a bunch of machines to handle it. And what we're saying with stateless code is that any one of those those copies of the code will give the same answer. Okay. The alternative with stateful code, we do have some memory. So the different copies of our code will have handled different requests in the past, and so their state will differ, and therefore they may give different responses to the same request. So, I'll show some examples of what those might be, but generally, when you have stateful code, what will happen is like you're changing state. Like let's say you're implementing a game, if the user is doing things in the game that's changing the state of the game, if that state of the game is stored in your code has become stateful, and so now when you make further interactions, when the user makes further requests to your system, like to get information about the game state, it needs to ask the same particular instance that it's been talking to this whole time, because that's the only one that has been keeping track of all the changes in the game state over time as you've been playing the game, right? Like if you've been playing the game with just that one instance, not with all these other instances. So if that's the way your system is designed, you still can scale horizontally, but you now have to have the clients, your users, make requests to the right instance of your code. So related requests, which generally means requests from the same client, have to go to the same handler, which is to say the same copy of your code. Okay. And I have a lot more slides that explain this in more detail. As an example of a stateful application, I'm going to illustrate here a network protocol that's stateful. SMTP is the simple mail transport protocol, I guess, or maybe standard mail transport protocol. Anyway, this is the mail protocol that was invented in the 80s. If you took my networking class, you would have seen this. So network protocol defines what messages, the format of messages sent over a network connection in order to perform some action, some service. In this case, it is sending an email. So on the right-hand side, you see a series of client messages and server responses. So the client messages are in black. So these come from the device that's sending an email. And the server receives those messages and sends back the green responses. So it's like there's a hello, there's a response to that, and then there's like line by line, the client provides information about the email message that it wants to send until finally it provides a lot of information, which is the actual message. And then finally the server accepts it and delivers it. So the server needs to remember, it gets the information about the message in chunks. It needs to store those somewhere, like in memory, and piece them together so that finally when the whole message is, when the last piece of the message, the text of the email is received, it knows, remembers who it's from and who to deliver it to. In this case, there are two different people who are receiving the message. There's some redundancy here because actually the envelope of the message that appears in the user interface is not quite the same as the information it's used to deliver. That's a weird feature of email, but you can just ignore the lower part down here. It's not super important. So this is an example of a stateful protocol. It was designed this way because SMTP was actually designed to be a protocol that you could type out manually as a user. And if you're trying to send an email to a friend, it's useful to be able to enter your friend's email address and then have the server tell you whether or not that was a valid email address before you go on and write your whole message. So there's some feedback. You could get an error code here if the recipient was not a valid email address. That's the reason why this protocol is designed that way. But it still retains that same stateful sequence of interactions, even 40 years later after it was invented. Okay, so a contrast to that is HTTP, another network protocol that is kind of a client-server protocol, but this is stateless. So in this case, the difference is that the request is just one request, not a series of related requests. And that one request, which an example is shown here, has all the information that's necessary to service the request, to give a response. And that means that this request can go to any one of many copies of the same web server, and the same response should be given. So this is a self-sufficient request. It doesn't matter what was previously sent from this client, this browser, to the web server. All that history is irrelevant. Everything that's necessary for the request is listed here. If there's anything from a previous request that is needed to fulfill a future request, it needs to be included as part of the message. And some of these headers are used for that purpose. Like, for example, cookies kind of carry over information from previous requests, and we'll see more about those later. So this is so there's a request as shown here, and here's an example of the response that comes back, and this response depends only on the information in this request. Okay, so we call that stateless. HTTP is defined to be a stateless protocol. Now, we can think back to MediaWiki, which is to say, Wikipedia, which we talked about in the last lecture, and ask ourselves whether it should be implemented as a stateful or a stateless service, a stateful or stateless application. Now, we talked about some of the things that Wikipedia does, and you probably can think of other ones, but just breaking down the steps involved in rendering a page, it involved getting text from the database, translating that text into HTML, adding some common wrapping content that appears on all the pages, and also adding user-specific information in the header, like your username and a link to edit your account and stuff like that. Stateless applications don't remember anything from previous requests, so everything that's needed to handle your request has to be included in that one request. Now, looking at these 4 different tasks I described here for MediaWiki, do you see any that have side effects? Or can you think of other actions on Wikipedia that would have side effects? Now, the goal here, we should approach this by thinking that our goal in general is to make a system stateless because it makes it easier to parallelize. But we are going to find cases where statefulness is needed, and we'll either tolerate that or we'll try to stamp it out by pushing the state somewhere else. But in your interactions with Wikipedia, like as a user, can you think of things that you do on the Wikipedia page that are stateful? In other words, you do something on Wikipedia. So physically you do something in the browser sends a request to Wikipedia, and that request actually causes the system to, later on when you do something else, give you a different response because you did something previously. What are some examples of those things? Stop and think about that. So, I'm going to go through 2 examples here of that. The first is editing a page, and the second is signing in. So those clearly are things that affect future responses, right? If you edit a page on MediaWiki, you're changing the content of a page. It's a community encyclopedia. Anyone can edit a page. When you're entering your edit in the browser sends a HTTP post request to the backend application, and those edits, those HTTP posts, should affect the results of future page fetches. So if I edit a page on a certain server, so remember Wikipedia is a huge service that has many clones of the application running in parallel, so it can handle millions and millions of users. If I'm on one server and I make an edit, then another user that comes in and visits the same page, whether it's on that same server or on a different server, that user should see the edits that I made. Okay, that's the challenge we're trying to solve here. So clearly, the edits I'm making should have system-wide effect. There should be some like state that is modified. The text of the article has to be modified. But is there a way we can do that, implement that, while still making MediaWiki stateless? So MediaWiki is the application that is implementing the back-end logic of Wikipedia. So stop and think about that. How can we do that? And how do we handle the propagation of these edits in general? And there are many different approaches, and it's okay if you can't think of it, but let me give you a simple answer is that you can solve this problem by using a database. So a database is a way to separate system state from stateless request handlers, or in general, a database is a central repository for data that's designed to be efficient in terms of both storage and access. And we'll talk a lot in this class about databases, like the middle middle half of the class kind of is devoted entirely to databases, different kinds of databases. But now we're kind of introducing why we would even want a database in the first place. So if we have a database, then all the things that are like need to be remembered and shared by the whole system can be stored in that database. And then you can have an application that sits above the database or in front of the database, depending on which way you're looking, that doesn't have to remember those things. If there's anything that an application needs to remember, it pushes it to the database. So the edits that the users are doing, the results of those edits are stored in an external shared database, and all the different copies of MediaWiki access that same shared database, so they see the same articles. They see the effects of everyone else's changes, and that database has to be queried, which is like, data has to be fetched from the database. That's called a query. Every time MediaWiki needs to build a page, because the data for the article is in that database. So the PHP code in MediaWiki can be stateless and easily parallelized if the things that need to be remembered over time are not stored in this PHP code. Like the PHP variables in MediaWiki are not remembering anything as a result of edits or anything. Anything that needs to be remembered is just pushed out to the database. Okay, so we push state down to a database. And that allows us to have a system where at least part of it is stateless, and that stateless part can be easily scaled. The system as a whole is going to have state. The state in the case of Wikipedia and MediaWiki, the state is the text of the articles. That's obviously going to change over time. As users do their things, the side effect is that articles change. Okay, but those changes are stored in the database, so that the bottom layer of the system, the upper layers of the system don't have to track that state. A second class of activities on MediaWiki, or a lot of websites really, that have side effects are sign-in. So when a user logs into a website, that's an action the user takes. It's an HTTP request that's made to the server. And after that sign-in action, like suddenly the kinds of responses you get are going to be different because they're going to be tailored to the specific user that you signed in with. Right? If I sign in with my username and password, then I expect in the future when I interact with that website, I'm going to see content that's customized for me. So if you just think about the system as a whole in that case, it is stateful, because what I get in the future, the responses I get in the future depend on what I did in the past. The thing I did in the past was sign in, right? Providing a username and a password that are correct. Okay, so how do we avoid... So we want to, of course, allow sign-ins in users customized content. And for MediaWiki, that includes like the header on every page that has my username listed with a link to my account information. How do I implement that while keeping that state, that sign-in state or user account state, out of MediaWiki? If I want to have that MediaWiki application still be stateless, how can I support sign-in? Stop and think about that. You may have some prior knowledge of this, or this may be a totally new thing where you just see what ideas you can come up with. Well, what we have to do here is, again, push the state out of MediaWiki and push it up to the client as well as down to a database, probably. And cookies are the way we do this. So a web browser stores cookies to allow for a series of requests to be connected, I guess, and to allow for a client to be identified to the backend server that's making requests to. So when you sign in, I have another slide that kind of gives an example of this, which should clarify, but when you sign in, you get a cookie from the backend, from the server that you're talking to. The browser stores the cookie, and it provides that same cookie in all the other HTTP requests that go to the same web domain. And then the backend, in this case MediaWiki, can use that cookie to figure out, to look up who you are. So the cookie is stored on the front end in the web browser. The cookie is stored in the back end in a database, although there is a trick you can use to avoid having to store it in the database, but let's ignore that trick for now. You really have to sort of know a little bit about cryptography, like either public keys or HMAX, which is covered a little bit in the networking class. But anyway, this is not super important. Let's just say the cookie is stored in the client side, in the browser, and also in the database, and checked. So here's an example of how it's used with login. So the user signs into a web page, right? So they provide their username and password in a post request from the browser. You fill out a form on a web page that sends a post request to a server. The server takes that username and password and checks with its database to see whether that's valid. If it is valid, then it now knows what user you are, and it wants to remember you in future requests. So what it does is it generates a random number called a cookie. It stores that in its database on the back end, and it lists both the new random number, the cookie, and the user ID or username that is associated with that cookie. And it also returns that cookie back to the user. So this here shows an HTTP response, a simplified response that you might get from a login request that tells you the browser to redirect to a certain page, and also to store a cookie. The set cookie header tells the browser to store a cookie. And by doing that, the browser will include that cookie in every future request it makes to that domain. So this next pink request is the HTTP GET request to load the page that it was redirected to. In addition to the normal information you would include, like that corresponds to the URL that you're visiting, which is somewhatwebsite.com/account, you're including that cookie. So like by now, suddenly what you're doing is linking the previous request with the next request. Because the server said, okay, in response to the first request, the server said, like, here's your response, and oh, here's a cookie. By doing that, it's giving the browser something that it can include in the next request, so the server can link the second request to the first request. And the way it links it is because it has stored this cookie in the database along with the user ID, so it identifies. So when this pink request comes in, the server can check in the database whether this cookie is valid, and if it is valid, it can see which user it's associated with. So it now knows that this request, even though this request includes no password or username or anything, it will know that this request could have only come from the user who previously successfully logged in with a certain username and password for a particular user, because it stored that user ID and this cookie, and the server generated this. This cookie becomes a password for this session, for this one browser. Okay. Now, given that information about cookies, would you say that HTTP with cookies is stateless? Remember, stateless means the server doesn't need to remember anything about previous requests in order to handle a given request. Well, the protocol is stateless still, because the client is actually providing the information that's needed to remind the server of who it is and what connection it has to previous requests. So this cookie header has to be included if this request is to be recognized. And no matter which of the many copies of the backend this goes to, even if you log in to server A, and server A gives you the cookie, and then you make your next request to server B. If you provide the same cookie, and that cookie was stored in a database that's shared by the two, then the second server will be able to give you the response that is appropriate for you. It will recognize that you've logged in. And this protocol, the HTTP protocol, is not doing anything. It's not remembering anything. It's not using anything other than what came in the request to generate the response. Okay, so we've been talking about statelessness. How does this help again? Well, let's look at Wikipedia, the MediaWiki application. In this example, remember that I showed you this before, the basic setup of Wikipedia, where they have 200 different copies or instances of MediaWiki, their main application, running behind a load balancer, really a set of load balancers. So all these blue donuts are copies of the application. There are load balancers in front. Load balancing is done by DNS and software proxies. We'll talk more about that in a couple more lectures. Any one of these 200 different, so these yellow donuts represent load balancers, and that's actually where the requests come in to, and then from there they're distributed to these blue donuts, which are the the applications, identical copies of the same application. Any one of those each one of these donuts actually represents a big machine with lots of CPU cores that has lots of threads. So actually each one of these can handle lots of requests in parallel. So this is a cluster of machines that can handle many thousands of requests at once. Okay. So these blue donuts, these application servers are stateless. They don't remember anything. If they need to remember anything, they store it in the database. These blue, green cylinders. That's always the icon we use for databases. So coordination only happens by writing to a shared database. So by making our application stateless, we're able to have 200 copies of it run in parallel, and for the request to be handed off using very simple logic in this load balancer to any one of them to handle it. Okay. Now I want to give another example to make a little more clear this idea of statelessness and statefulness, and to show that it's not totally you don't have to build your system to be stateless. You can have stateful services. And sometimes it makes sense to choose a stateful design of your service. But this example we're going to start with next is a chess website. So imagine something like chess.com. We have a lot of games happening at once, and every game has a game number, and let's say there's a page for each game. So if you want to make a move for a game, you visit a URL that I just made this up. That has the game number in it. So that URL, you've written some code for this web application in whatever language your favorite language is, in a web server, whatever is your favorite web server for your favorite language, that accepts GET requests and those GET requests generally will have the URL, /game number, and your code will use that number to look up in memory, it'll have, your code has some kind of a data structure, like a dictionary would probably be a good choice, that allows it to choose from many different ongoing games, and to get the information about that game, render it in HTML and return it back to the user. And maybe if the user provides a move, to make that move in the game, or to tell the user that the move was invalid, or to tell the user the game was won or lost or whatever. If this could also have some kind of artificial intelligence in here to allow the users to play against the computer, whatever. This is just an imaginary application. Now, the simplest design for this, like if you were taking a undergraduate computer science class, this might be an assignment you got to design a chess engine or a chess website. I think you could do something like that by the time you're ready to graduate. And you would probably implement it, like I said, to use some kind of in-memory data structure like a dictionary to store the information about all the different games, and do this in a way that you can handle many games happening at the same time. And this is all one machine, right? Okay. Now, that's all well and good, but let's say you want to scale this up to handle millions of users, okay? How would you scale this application? How would you scale it vertically, and how would you scale it horizontally? I want you to stop and think about this for a second. Just at a high level, just without too much detail, but what would it mean to scale it vertically, and what would it mean to scale it horizontally? Well, to answer that, just as a review, vertical scaling is just taking your machines and making them faster. So if you want to make this scale this to handle more users, you can buy a faster server that has, for example, more memory in it so that it can store more games in the dictionary. That would help you to handle more games at once. Or a faster CPU, or a CPU with more cores, so that if you're using like threading to handle requests in parallel, you could handle more games at once. But there's a limit to how fast you can go with that, with vertical scaling, remember. So eventually you have to scale horizontally, and to scale horizontally, you have to actually have more than one machine. Now this is where it gets tricky, right? How do you take your simple application that stored information about the games in memory and split it up across many machines? Because now the tricky thing is, where do you put the games, the information about the games? Now the first design I have here, the simplest way of horizontally scaling your chest application, is going to use almost the exact same code. Take almost the exact same code, or maybe literally the same code, and deploy it on several different servers. So now each one of these servers is still storing in memory information about games, but they're storing different games. All right, so so if you want to play a game, you have to like pick one of the different chess servers to connect to, and once you connect, you'll see your game. You know, the beginning of the game where no one's moved yet. You'll make your move, and then once you make your move, that move will be stored on that server that you were talking to. So if you're user 1, you're talking to this first server, your game information will be stored here. If you want to continue playing that game, you have to keep talking to that server, because the location where that game information is stored is in the memory of this server. So in other words, this is a stateful application. It's the side effect of the users taking actions, like making moves in the game, is that the memory on this application is changed in a way that affects future requests. So if later on another user fetches the information about my game, they'll see the move I made because my move modified the memory of this machine. Okay, and there also are games stored on all the different servers. By having multiple servers, of course, we can handle more load. We can handle an arbitrary amount of load. But the tricky thing is that each game runs on just one of the servers, so you have to like know which server to connect to play a particular game. And once you connect and start playing, you have to continue connecting to the same machine. Okay, so do you see any problems with this approach? There's some good things about it, like the fact that it's a pretty simple design, and it allows us to use our basic data collections that we have from our programming language. Like, if you're using Python, you have your dictionaries are available, and you can use that to store game information. And you can use basically very elementary programming techniques to implement this. Although I guess you would probably want to have threading, which is not a elementary programming technique. But if you're using a web server framework, then actually it takes care of the threading for you. In other words, like running your stuff in parallel. Okay, but anyway, can you see any problems with scaling in this way using stateful application servers? Well, I see a few. And I mentioned some of them, right? So the user has to connect to the exact same server to continue playing, which sounds okay, but how does that actually, you have to think about how that's really going to work in practice. Like, if the users are visiting a website like chess.com, so the web browser is connected to chess.com, that's one location. And so you might have to connect somewhere first, and that place you connect to has to direct you to the right instance. So that's we're going to call that a load balancer later on. That load balancer has to always connect the same user to the same backend server. Or you have to modify your URLs. Like you might have a prefix to the domain, like a.chess.com and b.chess.com and c.chess.com. Or you could do it by country. If you that would be one way to handle the load, like us.chess.com and uk.chess.com would be ways to create names that different users could connect to that would segment them automatically onto different servers to allow a kind of horizontal scaling. But it's not really like, it doesn't, it's a little bit hacky. So also, if a server fails, if this first server fails, it crashes or the hardware fails, then all the games stored there are lost, or they're at least interrupted if there's a backup and it needs to reboot. Yeah. And like I said, this is a stateful design of web application. Now, we saw some drawbacks there. There's some benefits there. I mean, the simplicity of it is one of the big upsides of it. But there's some drawbacks. So I want you to think about how to design the same chess application in a stateless way. So we can have a horizontally scaled system with lots of machines running the code, yet we don't have to worry about which one of them we're connecting to play any particular game. Let's take that as your challenge and think about that for a second. Well, if you've been paying attention and you remember what we were doing with Wikipedia, we're going to do basically the same thing as we did with Wikipedia. We're going to use a database. Okay, so we still have a lot of users. Those users connect to one of several different instances of the application. Technically, a load balancer is going to decide or be the intermediary that connects the users to the applications, but we're going to talk about load balancers later. Let's not worry about that too much for now. Just assume the user can connect to any one of these copies of the application. But the memory or the state of the game is not stored within these applications, but stored in a central database. So if a user is making a move on game one, that information is stored not on the web application they connected to, but in the central database. Okay. That is what allows the request. So a user that connects to the first instance can make a move on game one, and then a user connects to the last instance and reads and wants to see the board for game one. Even though it's a totally different copy of the application, it will still see that be able to access that information about game one, because that all the game information is stored in a central shared database. All right. So that sounds good in a way, but it also kind of feels like cheating in a sense, right? So do you see any problems with this approach? Stop and think about that. Well, I see one big problem, which is something we're going to talk about for many lectures. It is the fact that this database now is a central shared resource that will limit scalability. We now have, we designed our system, we wanted to have a lot of parallelism, to have many copies of our web application running in parallel to handle lots of users. But we're having them all talk to one machine on the back end to handle the data, to share the data. So this database is going to become overloaded very quickly if the system scales up and we're not careful about how we design it. So this will only work if there's a small amount of data. For example, if the representation of the chessboards is very compact, and actually for chess, that's true. There's not a lot of information to store about a chess game. That's different than, let's say, photos on a social media application. That's a ton of data, or videos, God forbid. And also, if there's a lot of computation that needs to happen, that would make sense that where you can have multiple web applications running in parallel, and that helps you to share the load. For example, if these web applications are implemented some kind of artificial intelligence to allow you to play against a computer, that can take a lot of CPU time and a lot of memory. So you might actually need, let's say, 100 different copies of this web application running the artificial intelligence to handle 1 million users, let's say. Yet the data associated with those games, the actual boards that store the game state, could be pretty small, and that could actually really effectively be stored in a single shared database Yeah, to store the games for every chess match in the world could probably fit on your iPhone, on your smartphone. So we're not talking about a huge database for chess, right? That's an application where a single central database makes sense. There's another component of the system that does require lots of machines, but that's a stateless component. Like the AI is a stateless thing. The AI just needs to look up the current state of the game in order to have all the information it needs to build out what the ideal next move is for the computer. Okay, so that was chess, and that's the lecture. So to review today, I talked about stateless services and stateful services. We showed how databases and cookies allow an application, this is like a traditional 3-tiered application, to push state up to the browser with cookies and down to the database, allowing that middle part to be stateless and easily parallelized, and allowing all those parallel workers to be interchangeable. So we achieved parallelism and distributed execution with statelessness, and that allows us to avoid difficult coordination problems because we're pushing the difficult coordination problem down to a database. So like whenever we need to coordinate anything, it ends up being something that's stored in a database that everyone checks. Okay, and then so that creates problems we have to solve later because we now have this performance bottleneck in a database potentially. We need to figure out ways of making databases really fast and choosing the right databases. And we also need to figure out how to direct users to a particular instance if we have many instances of a service. That's called load balancing. That's not so bad. We'll talk about that. There's several ways to do it, but it's not like super complicated. And overall, we have like one big lesson here today. The first lesson of scalability, I would say, which is don't share if you don't need to. So when you're a kid, your parents try to teach you how to share. I'm going to teach you not to share. Okay, at least for building a scalable system, if at all possible. If you can avoid sharing data, that means that you can operate independently. You don't have to worry about what your neighbors are doing if the things that your neighbors are doing don't affect the things you do. Okay, and that's what stateless workers, stateless services are doing. That's why we try to make things stateless. Okay, so I hope that made sense. Next time we'll talk about caches and proxies, load balancing, that kind of thing. All right, see you later.